Okay, I like to stand up when I talk. Somehow, if I sit down and talk, I fall asleep. Yeah, please. So, I think the recording has already started. So for those of you who just came, I just want to mention that I put the slides on my web page there, but the slides will probably change a little bit each time as I think of things to change or add. And so I'm from the University of Wisconsin. I was born and raised in Singapore. Went to Berkeley for my PhD in statistics, and then went to Wisconsin in 1978. No, I went to Berkeley in 1978 and went to Wisconsin in 82. And now it's 2022. So I've lived in Wisconsin for 40 years. And during that time, I've had 3 kids and 7 grandchildren. Okay, but not all in Wisconsin, of course. So I've never been to Cambridge. I've never actually been to Europe. I've been mostly to Asia. So I'm very happy to be here. And I'll be talking about something that I have spent almost the whole of my academic career working on, as far as research is concerned, classification and regression trees. Let me see. Okay, so just to maybe let you know about my background in this research, I'll just mention a chronological list of the major algorithms in regression trees. As you know, nowadays regression trees is considered part of machine learning. In fact, it's actually quite a useful or important component of machine learning. But the very first algorithm came out in 1963 from the University of Michigan. They were not invented by statisticians or mathematicians or computer scientists. At that time, there was no such thing as computer science. When I was an undergraduate in Singapore, there was no computer science department. So in 1963, a group of people at the Survey Research Center at the University of Michigan, which is a very big, famous survey research center, it still exists. They have been analyzing survey data for the government, and they have not been satisfied with the tools available at that time, which was just linear regression and logistic regression. So they came up with this idea of a decision tree. And they published a paper in 63 called AID. It's not AIDS, but AID stood for automatic interaction detection. The idea is to detect interactions by looking at the different variables that are used to split the sample space. And that was a regression tree algorithm. A few years later, they published another paper called THEID, which was classification. So you notice in the title of my talk, I mentioned classification and regression trees. They are all trees. They are all tree methods. In the regression tree, the y variable or the dependent variable is a continuous variable. Okay, although I should say an ordinal variable. So it includes Poisson regression, for example, which is not, no, Poisson is not continuous. In a classification tree, the y variable or dependent variable is a class variable, like a factor variable. Okay, you can predict somebody's race, maybe. That would be a factor variable. If you're the R type of person, they call it a factor variable. So that's a distinction between classification and regression. Although if your y variable is binary, as I will talk about in the first example on death from COVID-19, a binary variable can be treated as can be analyzed using a regression tree, in which case the y variable will be actually probability of death. So it's a decimal between 0 to 1. Or you can do a classification tree which just predicts whether the person will die or not die. And then that y variable will just be a factor variable with 2 levels, right? So in 1963-72, this thing came out, and I think the first paper was published in JASA, one of our most prestigious journals, but it was hammered by statisticians because these people were not statisticians. There was no theory, there was not much math. They were heavily criticized and became like a leper. Nobody dared to touch it. Until 1984, when Bryman, Friedman, Ocean, and Stone, 2 from Stanford, 2 from Berkeley, came out with CAT. So I got my degree from Berkeley in 1982. So I was like a guinea pig for CAT at that time when I took a course on Bryman, because I think we were being used as beta testers for the software. So that came out in 1982, and the whole thing changed because here are 4 giants in statistics, and nobody had a peep of criticism. Nobody, except me. So what happened is that 1984, the book came out. So in the fall of 83 or spring of 84, I got a letter from the publisher saying that if you would teach a course based on this book, you get a free copy. I was like a second-year assistant professor. And wow, you know, I love books, and they were not cheap. They're still not cheap. And so I volunteered to teach a course. Now, being a second-year assistant professor, teaching a group of graduate students, some of the students are older than me. And I'm sure some of them was wondering, how good is a Berkeley PhD? You know, so I really studied the book so that I could act as if I'm an expert. And because I had to study and regurgitate the stuff, I really had to think about it. It's different from you reading a book, you know, just to learn the stuff. You know, if you have to learn it and teach it, it's a different story, right? And then I found all kinds of difficult problems, which, you know, during the course of these lectures, you'll see. And so I had my first student work on some ideas, and we published a paper. So I started working on it in, well, I started teaching the course the spring of 85, January. And I recall, you know, Wisconsin is very cold in the winter. And if you're an assistant professor, your parking spot is very far from campus. Now, my spot is right in front of my door because I'm 70 years old, right? So you have to wait your turn. So it's a long walk every time to class. And during that time, when it's so freezing cold, you have time to think. Because I was thinking about my class that I was going to teach. So that's when I came up with all these thoughts, right? So this 8 lectures is basically about the history of the development of my idea and my ideas. So that came out in JASA in 88, and it was severely criticized. It became a discussion paper. Never expected to have a discussion paper in JASA, but it became a discussion paper. The discussions were Bryman and Friedman. It was just I was just hammered saying that what I did wasn't right. Okay. So I basically I did a cheapskate way of doing it. I will in this. So there are many ways I can teach this course. I've taught this course so many times. I've taught it semester long, 15 weeks, 150 minutes a week. I've taught it like 8 lectures. I've taught it for 2 lectures. I've taught it for half a day. So there are many ways I can teach it. I'm not going to teach it chronologically, although to me that's quite exciting. But because of the time, I'm basically going to teach you the most recent things. And then as and when the chance comes along, I will tell you what other people before me did that was not so good. Right? But anyway, on this one, I'll just briefly tell you what is the idea. You all know linear discriminant analysis, right? Linear discriminant analysis is for classification, right? So the Fisher-Iris data, you all know about the Fisher-Iris data. That was what Fisher used to illustrate linear discriminant analysis. He had 3 types of flowers, iris flowers, setosa, versicolor, and virginica, right? And he had 4 measurements, 4 X variables. So the Y variable is the type of flower, 3 types. And he wanted to partition the space, this 4-dimensional space. The 4 variables were length of the petal, width of the petal, and sepal, width and length, right? So it's 4-dimensional space. So imagine now you have, so he had 150 observations, 50 from each flower. So now imagine a 4-dimensional space in which there are 150 stars in this galaxy, 4-dimensional galaxy. 150 stars. 50 of them are yellow, 1 flower. 50 are green, and 50 of them are red. You want to partition this space so that one of the polygons is mostly consists of red flowers, the other one green. So you want to sort of partition it into 3 regions so that, so that to sort of purify the regions. And Fisher's idea is just linear discriminant analysis, which is an eigenvalue problem, which is very fast. It's a matrix problem, right? And it's also very accurate. You know, if you have used linear discriminant analysis, you know, even if you compete against a neural network, unless you have some really weird nonlinearities in the data, linear discriminant analysis is going to give you a pretty decent accuracy rate. Now, CAT, if you apply CAT to this iris data, you have 4-dimensional space. CAT will partition this space using partitions that their axes are orthogonal. They are perpendicular to each axis, so that each split can be expressed in terms of one variable, x3 less than 5, something like that, right? In linear discriminant analysis, they are not like that. They're linear combinations. Not only are they linear combinations, the split is not a linear combination, not a split on one linear combination. You have 3 linear combinations, which are basically distances from where you are to the class centroids, and you classify to the one that's the centroid that's nearest to you, right? So it's a very ugly kind of thing, but it's a tree, and so as I was teaching this class back in 1985, I found that the CAT algorithm was really slow, really slow. I gave a homework problem on the Fisher iris data and let the students use CAT. There were 12 students. At that time, the University of Wisconsin Statistics Department had the largest departmental computer in the US, the largest for a statistics department. It has the largest departmental computer. Before that, everybody had a central computer, right? So we had the largest one. We're very proud of it, about it. I gave this problem to the students, and the next day, nobody could log in to read email. Nobody. Just 12 students analyzing this matrix with 150 rows and 4 columns. The 5th column is the Y. And it was running the whole night. Of course, I should tell you that this superpower computer had a standard 1 megabyte of RAM. 1 megabyte. We had to spend $5,000 to up it to 2 megabytes. $5,000 per megabyte. Nowadays, I think if you want to buy 1 megabyte, you probably have to pay more than 5,000 because it's not available anymore, right? So, but it was slow. But at the time, linear discriminant analysis could run right away. So I started thinking, can I marry the two together? Can I have a tree and yet the accuracy and speed of linear discriminant analysis, right? And as I started thinking about it, if I just apply linear discriminant analysis, I could write a very short tree, which only splits once, into 3 branches. It's not binary. 1 branch for the red flowers, 1 for the yellow, 1 for the green, right? Of course, not all data sets are as nice as the iris data for linear discriminant analysis, right? Sometimes things, for example, suppose in this 4-dimensional space, the reds are inside a sphere and the yellow are around that sphere. Now, linear discriminant analysis is not going to do well, right? But what happens if I just use it anyway? So it will cut. So imagine now my 3 colors are concentric, the worst case, one of the worst cases, right? The reds are in here, the blues are in here, and the greens are here. I apply linear discriminant analysis. It will cut into 3 parts. It will be terrible. But once I cut it, each part will not have the symmetry anymore. It's the symmetry that kills LDA because the centroids are close to each other. You need the centroids to be far apart, the class centroids, to have good cuts. So suddenly I thought, what about recursive LDA? Right? Do it a couple of times. Okay. In terms of speed, if you do a couple of times, it takes twice as long. So, okay, LDA takes 1 second. Now you take 2 seconds, or 3 seconds. And if one shot LDA is pretty good, I think if you do it a few times, it can't suddenly be terrible. So that was my idea. But then it doesn't look nice. First of all, the tree has 3 branches, and the splits are not on one variable at a time. And then I started thinking, oh, what happens if Fisher did not collect 4 variables? If he only collected 1, only x1, I could still apply LDA on x1. It's just one line. What does LDA do really when there's one line? LDA is maximum likelihood. You assume each class has a normal distribution with same variance, like a 2-sample t-test. This is like multi-sample, right? And then the cuts will be just the midpoints between the estimated centers of the normals. That's one-dimensional LDA. And then you would get a split on x1 that says if x1 is less than 2, is this side. If it's bigger than 5, is this side. In between is this one. And then naturally the question now is, if you have 4 variables, what do? Variable selection. Why don't I somehow find which is the best variable to do one-dimensional LDA? Right? And how do you do one-dimensional? How do you choose the variable? So maybe I can draw something here. Am I going too fast? No, okay. So here is, if you only have x1, right? Then these are estimated class densities. If everything is the same, is equal, right? Then you will cut in between midpoints of class centroids, right? So now this is x1, and now I have x2. Right? I can still find the centroids. This is centroid here, centroid. Right? And then I can cut it here. Right? So now if I split on x2, the result wouldn't be very good because there's too much overlap. Right? So it's obvious from, I can see everybody agreeing with me because your eye and brain is so powerful. You look at the pictures, you can tell that you should split on x1. How do you tell a computer to see that? Computer cannot see that. Computer can draw the pictures for you to see. The computer doesn't have that insight. But the computer can compute. So we can calculate the ANOVA F test for each x. The ANOVA F test is a test for separation of the classes. I want them to separate. I want to choose the variable where they separate best, minimal overlap, and then I choose to split on that variable. So that's my 1988 paper. Okay. Given any number of variables, just run ANOVA F test, find the most significant x variable, apply one-dimensional LDA. Super fast. And if you don't have this kind of things, if the class is like that, right? Say this is x1. So suppose we only have 2 dimensions, right? I cannot draw more than 2 dimensions, right? Suppose you pick x1. Here, it doesn't matter which one you pick, right? So you pick x1, it will be terrible because the class centers are, maybe it's like, I don't know how to draw it, right? So the first split is like this on x1, right? What happens with this region? This region is here. In this region, if I rotate this x2, there are half moons, right? Now, if I cut it again, there's still symmetry here, 3, right? Now, this part here will be very nicely, LDA would do a pretty good job of slicing up. Basically, you let LDA do its stuff, okay? And the only question is, when do you stop? if you keep going, it's going to overfit, right? So at that time, we just did something very naive. We are doing ANOVA anyway. So we each time when we do ANOVA, we see how much improvement we can get. And at some point, it's like stepwise regression, you know, F to include, F to exclude. So we have something it's just a hack, okay? So at that time, it was like the early days of Hyundai. Now, Hyundai is a respectable brand. Early days, people laugh at it. It's like early days of Hyundai competing with the Mercedes. Okay, so that was. Yeah, because I want a car that looks like a Mercedes. I didn't want a 5-wheel car. The Mercedes has 4 cars, so I want to have a car that has 4 wheels. So I want to make it axis orthogonal, so that I do a variable selection first. Yes.
So the second example shows that even when you split on bad variables, it eventually still works out.
Yeah, eventually. So eventually, the accuracy will be recovered.
So is it really important to choose a good variable in the beginning?
That's a very good question. That comes to interpretation. I just came off an international grants review panel for another country, and that was a review panel for mathematics, engineering, computer science, and so forth. There's so many proposals on explainable AI. You all know about that, right? It's very hard to explain AI, okay? And so Varun, you asked that question. Is it important what you cut? Depends on whether you want to understand what's going on, or do you just want to predict, okay? If you just want to predict, there are many methods, black box methods, and they're all very good, okay? But if you want to try to understand what is causing this good prediction, what variables are being used, then it's quite important, especially when you have a tree that shows the splits, that you don't mislead the reader. And one of the problems with regression trees that I'll discuss is that everybody says it's interpretable. Nobody attacks it being misinterpretable. People only attack it for accuracy. But actually, it's so easy to misinterpret a decision tree because it's, I mean, you look at it, it just sucks you. It's like a kid seeing candy, they must eat it. I mean, you don't have to tell them how to interpret it. They see it, they think that they can interpret, right? But that's the danger is, okay? So, yeah. Yes.
Do you have any theory for this, or is it just an algorithm?
The theory, okay, that is asymptotic theory, right? So in the Bryman book, they proved that for regression trees under some regularity conditions, it's base risk consistent. Base risk consistency, you know what that means. It means that if you know the true priors, that's the accuracy you get. With regression trees, they proved this theorem. It's the last chapter of the book, or maybe 2 chapters. That's in the 1984 book. That's accuracy, not interpretation. There are no theorems on interpretation because interpretability is the concept is not well defined. In my papers later on, Prabal Chowdhury, Varun probably knows about him. He is a very smart Indian statistician. He helped me prove point-wise uniform consistency. Okay, uniform consistency over compact sets. And you cannot have uniform consistency for minus infinity. So under some regularity conditions, okay, if you're trying to estimate expected value of y at any one point, okay, under some conditions, these methods are not specific any algorithm. Of course, the trick is how to check those conditions, but under those conditions, which are fairly standard conditions, they are point-wise uniform consistent. So rates are very difficult. Maybe Varun can prove it, or maybe my newborn granddaughter can prove it one day. But yeah, rates are very difficult because the whole thing is non-parametric, right? So, in fact, I think I'm glad you asked that question. In fact, that's why at least I found in all the simulations, all the examples, that accuracy is not very poor. I mean, they're not going to be the best all the time, but they're decent. Okay, and that's the reason, because there's some theory behind it. All right, so C4.5, I don't know whether you heard of that. That was a very famous computer science algorithm. It was very famous because the code was published, printed on 120 pages of a book. So that book, half of that book was C code, literal C code, and people actually type that in to use it. But nowadays, you can Google C4.5, you can get the zip tar file, okay, for the C code. So that became like the benchmark. Everybody who wanted to study trees would compare against C4.5 because the code is there. So, so later on, 1994, I wrote a paper with Probal Chowdhury helped us do the theory. But this paper was on regression trees, where we have piecewise. So the regression trees that people think about are piecewise constant. You cut the space, and in each terminal node in that region, you fit a y bar, you fit a constant. That's piecewise constant. Sometimes, if the true function is just a plane, you have a huge tree because it's trying to approximate to the staircase, right? And you'll be thinking that, wow, there's a lot of complexity, but it's just a plane. So my idea there was, what if we fit a plane to each node, right? And the card method cannot do that. Conceptually, it should be able to do that. But if it had so much trouble on piecewise constant on iris data problem, they cannot fit the plane at every node. The amount of computations there. But I was just doing simple things, so I could do that. So that was 1994. And then we came out with these two papers, which showed there's a fundamental problem with CART, selection bias, which is what Varun was asking. They would select a variable to split the nodes just because there are so many ways to select that, to split that variable. So remember these stars in these three colored stars, right? Three colors of stars in this galaxy, right? If we only split on x1, then how many ways can you cut this space in this galaxy on x1? One less than the number of sample points, assuming they're all distinct, right? But suppose I say these stars are not just located by their Euclidean coordinates, but some of these stars belong to certain classes. They're members of certain clusters. So like occupation. So think of our data as hospital patients, right? Besides blood pressure, weight, height, and so forth. We have their occupations. Now, what CART will do when you have a categorical variable by occupation, you look at all subsets to purify these stars, right? So if there are C occupations, the number of subsets of occupations is 2 to the power of C, something like that, exponential, right? So CART will just love these variables, okay? So for example, here's a very simple example. Suppose I'm trying to predict when someone dies from COVID-19 or does not die from COVID-19, right? And I have all this information about their comorbidities. But I also have the occupations. And suppose everybody has a distinct occupation. CART will just find those who died, find out what their occupations are, and say, here, if you split on this set of occupations, everybody dies. The complement, everybody survives. And you cannot beat that split. It's a pure split. Right? Nobody will believe that your occupation is more important than anything else on your mortality. If you split on age, there are only so many ages you can cut on, right? But on something like occupation or telephone numbers or zip codes, you have zip codes. People will think, oh, there's some geographical, this part is really terrible for COVID-19. It's all BS, right? It's just because you allow so many degrees of freedom on some variables. Whereas something like gender used to be there only 2 genders. Now there's non-binary, okay, 3 genders, right? With 3 genders, there are only 3 ways to split. right? How do you compete against something like occupation? Right? Okay, so I'm jumping ahead here. So I can be very fluid. Okay, so what this means is that we're going to skip a lot of slides in the meantime. So, with this Quest paper, and then follow up with the Cruz paper, we demonstrated that CAD has this fundamental difficulty. And by that time, Leo Breiman, I think, realized that. And then he came up with random forest. And he started bashing CAD. You know, first 10 years after CAD was released, they were praising CAD. Best thing since sliced bread. But by 2001, he was saying, he didn't say CAD is bad. He said the whole concept of classification and regression, trees are bad. Forests are good. Okay, and so, and then I came up with my own algorithm. So you see that maybe I can ask you one question, give you a quiz. I have to find names for the methods, right? So I called one method support, one method quest, one method cruise, one method guide. What's the connection here? Just look at the letters of these words. The U, the letter U, you know about Sesame Street, right? You don't know? I mean, there's American children's program. The letter U, unbiased variable selection. So I wanted to tell people that these algorithms of mine have unbiased variable selection. Okay, then later on, so I did this for regression, I did this for classification. Part of the reason I came out with a guide is by that time, okay, all my students have graduated. You know, those who helped me, like this first student of mine, she became department chair, then she retired. I cannot ask her to keep maintaining the code. They have their lives of their own. Right? So every one of my students became department chair and so forth, deans and so forth. And it's very hard for me to ask them. I did ask them, can you add this and that? And it takes longer and longer and longer for the response. And so I decided I'll do it all by myself. So now guide is conceived and written in Fortran all by myself. 20,000 lines of Fortran. It took me many years, but so I first did it for regression, then I extended it classification, and there are these methods. I don't know whether you're aware of them. They are from this R package called Party. They're from a group of German people. They were students in Germany, in some university in Germany, a group of students like you guys. And at that time, they learned about my methods. They wanted to write an R version of it. God help them, because my code is a living code. I mean, you know, I could add things on the airplane if I want to change some things. So in the end, they gave up, and then they all graduated. They're all professors now in Europe, Austria, Germany, and so forth. And then they came up with their own R packages called C-tree for conditional inference tree, and MOB stands for model-based tree. I'll mention something like that. So later on, I kept working on it. This paper extended to multidimensional Ys. So it's not just one Y. We could have multiple. For example, if you have a longitudinal data and your Ys, patients come in every month to get their blood pressure taken, right? And then you want to look at trajectories. So that's multidimensional. And then this is a subgroup analysis. You were saying you're going to do subgroup. Okay, so I did that. That was the first paper. This is on missing data. Lately, I found out that one of the strengths of Guide is how it handles missing data. It can handle missing data without imputation. And nobody believes that. You know, if you have missing data, most people have to impute them before they proceed. With Guide, you don't have to do that.
What do you mean when you say it
can predict. So you have a Y and you have X's. And the X's have missing values.
What's that?
Doesn't have to be at random. So here's an example. If you look at survey data, so the data I was looking at was from the Bureau of Labor Statistics. They do a quarterly survey and to look at the economic pulse of the country in the US. And they do a person-to-person interview. And one of the variables is the age of the respondent, the person who answers the interview. Another question, and that one has no missing data because it's person-to-person. Another variable that has 40% missing is age of spouse. Why do so many people not tell you the age of their spouses? Because they do not have a spouse. You impute that, then your sample no longer looks the same as your population. Right? You impute that, you no longer know that this person is unmarried. It's gone from the data. Why do you want to impute it? Because you want to do logistic regression. Because you want to do linear regression. Because age of spouse is a continuous variable, so-called continuous variable. You want to use it, it has to stay continuous. The imputed value has to stay continuous. In guide, you don't have to do that. In guide, I'll get back to this example later on, which I may not have time. In guide, if you split on age of spouse, it will say, okay, if age of spouse is less than 40, go to one side. Bigger than 40, go to the other side. Those who are missing will either go to the right or the left. The algorithm will decide whether those who are missing age of spouse are more similar to the people with young spouses in terms of the Y variable, or more similar to the people with older spouses in terms of the Y variable. Age of spouse is missing, but the Y variable is not missing. If the Y variable is not missing, that case cannot be used. So that's information. So now you have a tree that can still filter the data without you having to plug in a fake number. Right? What do people in survey research do? They have a separate model. They say, oh yeah, we know about this. We don't impute. No. We have a separate model for those without spouses and those with spouses. What about people with no children? Yet another separate model. How many separate models do you build? Okay, so survey data is well known to have a lot of missing data. Another data set, a type of data that is now very common. People in computer science use it a lot. Electronic medical records, EMR. Those have a lot more missing data. And they're not randomly missing. They're missing for some reason that we don't know. Some hospital systems don't collect them. Some doctors are not told to collect them. Right? And some of these variables are missing because the patient is so sick. Answer your question. Now you start to impute. Yeah, that will get your logistic regression and linear regression going. But you lose all this information. You just fudge them. Right? Okay, so that was that. And 2020 was a follow-up paper on missing data. And then we have this one, which is variable importance. So I used to think, CAD was really ahead of the time. In 1984, they had a ranking of variables in order of importance. To me, I always thought that this is a concept that's ill-defined. What do you mean order of beauty? How do you define beauty? What do you mean by important, right? Is my heart important for my health? Yes. Are my kidneys important for my health? No, not if one is still good. Or even if I both good, I can donate one. Does that mean my kidney is not important? You see what I mean? No. But people, a lot of people trying to do interpretable AI. The first question they try to tackle is variable importance. They want to rank the variables so that at least they can, if they cannot explain how each variable is used in their model, they can say that these variables are used, right? Now, if you do it that way, then your variable importance concept is tied to your algorithm. Do you want to define it that way? If you define it that way, then everybody has different importance scores because everybody uses different algorithms. So these are ideas I've been struggling for almost 40 years. Okay, I hope to share some of what some solutions I came up with. And this is the latest paper. This paper has been always to appear because it's in a Springer Engineering Handbook of Statistics, and that book somehow, because it's a compendium of hundreds of articles, it never could see the light of day. So since 5 years ago, they were saying it's going to be published, and still somebody's sleeping somewhere. My paper has already been finished. That is logistic regression trees. So in each node, we fit a logistic regression curve rather than a constant.
So these structures, they are all so from random forest downwards, are they all ensemble methods? Or do you still have...
Oh, no, these are all tree methods. They have ensemble components. So guide also has ensemble. So if I get a chance to demo guide, which I hope maybe the last lecture, but maybe not, you have a choice. You want to build a tree or you want to build a forest. So if you want to build a forest, guide will build you, by default, 500 trees. You can change that. And then it will average the predictions and come up with a forest prediction.
Can I ask a question?
Yeah.
You don't mention boosting. Is there a reason for this? I mean, I feel like they're also quite popular.
I feel that, unless you're talking about boosting trees, okay. I feel it's unnecessary because I think boosting, if you boost a tree, that means you somehow take the residuals from this tree and grow another tree. And that they interpret two trees, right? And one side boosting may not be enough, you boost a few more times. By the time you have a forest, I would rather the forest. Right? Because I've not seen any evidence that boosted trees can beat a forest. The forest is simple and fast. Okay. For boosting, for regression trees, yeah, you can take residuals and boost the residuals. But for classification, you have to define residuals for classification. Some people define it to be the mistakes you make, right? So no, I'm too old to add boosting to that. Yeah. Besides, it's 220,000 lines of code. If I add a big thing, everything else will be, changed. So I have to keep track of the clock, and I'm only on slide 2. But I think that's better than for me just read through the slides. So here's the outline finally. Okay, I'm going to have this example, which I was hoping to cover today, COVID-19, and then I will go on to some of the main ideas, which actually I really touch upon. So when we go to that, we can go faster. And selection bias, I have some examples. Each of them have some examples: missing values, importance scoring, Poisson regression trees, censoring, subgroups with differential treatment effects. That's a breast cancer example. Longitudinal response, clustering, cyclic or angular predictors. Sometimes you have variables at angles. So my example here is vehicle car crashes. So when the government will test the safety of cars by crashing them. They do not always crash them head on, they crash them at angles. Then this is an angular variable. How do you deal with an angular variable? All right. I solved that problem with a tree. So basically, if it's a x1 continuous variable, you cut at some point. If it's a circle, you cut a sector like a pizza slice. Right? You take out a pizza slice. So guide is the only method that can handle this kind of circular variables. And they're not just always angles. It could be day of the week. Weekends are different, Saturdays and Sundays. Right? If you quote Sunday as 1 and Saturday as 7, then they're like very extreme. But actually they are more similar. Right? So guide will cut us. If it's really a weekend effect, it will just slice out Saturday and Sunday. And then point number 10 is observational studies. Many of these subgroup analysis methods are clinical trials randomized, so that's easy to assign causal effects. But sometimes nowadays you have observational studies which are non-randomized. Okay, and people still want to estimate the average treatment effect. That means you control. So you have propensity scoring and all this stuff. So what I'll be talking about. And post-selection inference, which is the most theoretical part of this lectures, is after I get the tree, right? If you fit a regression model in the node, you get the coefficients. People want to know how significant are those coefficients, right? So you have a beta slope, say you have a slope in every node you have some slope beta. People want to get confidence intervals. And for a long time, I felt that problem is impossible because there's no beta in the true data. It's all non-parametric, right? And we split this based on a random sample. So the model you get is sort of random in the sense that the data are random. You will never see it again. So how do you get confidence intervals? Right? But I solved it with Bootstrap, with the Bootstrap method, which actually very interesting. My first paper, I've been working on Bootstrap before I started working on this. My first paper on trees was 1988. In JASA. In 1987, I published a Bootstrap paper in JASA. It turns out that is where the solution lies. So I had two different lines of research, Bootstrap and trees, and for most of the time I followed this. In the end, turns out that this came out like a knight on a white horse or a white knight coming to the rescue. Okay, all right, so just a few minutes. Okay, so here's a data set, 31,000 patients hospitalized with COVID-19. From the first, I think, 5 months of the pandemic in the United States, I took this from some website, some people analyze this, and there are 21 variables. One of the variables is the death from COVID-19. The mortality is only 4%. It's very, very low. There are 5 age groups. They should have just recorded age, but they group them into groups. Group 0 is 0 to 59, then 60 to 70, 70 to 80, 80 to so forth. Why did they do that? I just hate it when they do that. Well, they did that because they want to use linear regression, and they know the age is not a linear effect. So they chop it up. Okay. Then there's sex, then race, and 15 comorbidities like cancer, myocardial infection, and so forth. And then there's a measure of a comorbidity index, which is just a linear combination of all the indicators for the comorbidities. So these are the variables. Diet is the Y variable. Age category, you can see that it's coded into 5 categories. Race, sex, then whether you have AIDS or not, it's 0, 1. Whether you have cancer, whether you have cerebral vascular disease, congestive heart failure, chronic pulmonary disease, dementia, diabetes, whether you are half paralyzed or fully paralyzed, whether you have a metastatic solid tumor, myocardial infection, liver disease, peptic ulcer, peripheral vascular disease, rheumatic disease, renal disease, and then there's Charlson score, right? So now you see this Charlson score is linearly dependent on all the others. If you fit linear logistic regression, you either use Charlson score and nothing else, or you use the others and no Charlson score. Otherwise, you get perfect. Yeah, but guy can use all of them. Okay. So here, just to give you some pictures. On the left, on yellow, is the mortality rate. The baseline is in red. That's 4% mortality. On the right is just a distribution of counts. So you can see that males are more at risk of dying, but there are more females in the data, the blue on the right. Okay. For mortality, you see, yeah, the old people, at least in the early part of the pandemic, they tend to have higher risk of death, but there are fewer of those very old people on the right. Okay. So, and this is race. So there's a huge chunk of unknown race. Okay, unknown. With Guide, you don't have to impute it, just treat it as unknown. Even for logistic regression, you can treat it as unknown. So in logistic regression, you only need to impute if it's a continuous variable. But if it's categorical variable like race, you can leave it as unknown race or other race, and you can still go with that. And so now I have all the comorbidities, and you see, basically, if you have any of these comorbidities, your risk of dying, look at the yellow ones, your risk of dying is increased. Okay. If you look at the blue ones, there's a frequencies of people with such diseases. So you find that the yeses are very, very small amounts. And it's cancer. So the picture is pretty much the same. Okay. So what we want to do is we want to build a model to predict probability of death. And also you want to ask, is it easy to interpret the model? And most people will just say, oh, logistic regression because y is 0, 1. And this data has no missing values. That's why they published it. So they don't have to mess with that. I don't know what they did with the data, missing data, maybe threw it away. Okay, but this is really clean. But is the model easy to misinterpret? Yes, most models are. How do you guard against that? And then subgroups, which are the patients at highest and lowest risk of death. And I know I'm now guilty of exceeding the time, but maybe I'll stop with this. This shows you a regression tree. It's trying to predict this probability of death, which is decimal. It says, so that tree has at each intermediate node a condition that I wrote on the left. I wrote on the left because if the answer to that condition is yes, you go to the left. That's why I put it on the left, right? So an affirmative, so age category less than or equal to 2 is actually age less than 70, real age less than 70. So the people who are age less than 70 will go to the left. And the next question is, do they have renal disease? 0 means no, all right? So if you do not have renal disease, you go to the left. And then the next question is back to age category. Are you younger than 60? And the top is, are you younger than 70? Right? Are you younger than 60? And if you're younger than 60, you're here, and your estimated probability of death is only 1%. The baseline is 4%. So these are people who don't have renal disease and who are younger than 60. The blue color, if you look at the last line here, if a node is colored blue, it means it's below the baseline rate. You see a lot of yellows, right? But you also should notice the sample size. We have 31,000 patients, 20,000 are there. That's why there's only one blue. It's a huge node, right? So if you go down this path, those are people above age 70 who have a Charlson index of bigger than 1. That means 1 or more comorbidities. And more than that, they have renal disease. Okay, and their risk is 6 times above baseline, 24%. The sample size there is 1,298. Right. So this is what a regression tree looks like. You can say it's interpretable, but I should not keep talking. I'm supposed to stop. All right, so I'll stop here and I'll come back on Friday. I'm supposed to teach this class every Monday and Wednesday, but Monday I was involved in this review panel that was started from 6 a.m. local time to 10:30 a.m. There's no way I can run here to teach. So that's why for this week is Wednesday, Friday. The next 3 weeks will be Monday, Wednesday. Okay, all right, thanks for coming.
Pretty sure.